on the interval a to b. So the beginning theorem says, I want to say it says that it's continuous on the interval a to b. There's different ways around it. But basically your function is nice on some interval a to b. What is the derivative of this form when you integrate from a to x? Then it would just be f of x. So why do I mention that? What if I wanted to find the derivative of the integral from x to b, or x to a? I will say b. What would that be? We'll do that. Yeah, what would I need to do? The negative sign. This is the same as negative the derivative from a to x. I get a negative sign right when I put a on the bottom. So now this becomes negative f of x. Again, for a less than x less than b. So when we write this, we're really always thinking a is my starting point, and then I'm moving this direction. So we'll get back to this in a little bit. But actually, yeah, go back to this a little bit. The reason I want to mention that, for an example, we're going to do it a little bit. Alright, so some other ones just as reminders. Let's say y is equal to the function integral from x squared to 1 of the natural log of t dt. Find y prime of x. So how do we do this? So I would say find the derivative of this. So what would we do?
The first step would be a constant. So we would go down to 0. So you only really
Yeah, we're getting to the same place here. We always want the constant on the bottom, so he said do negative integral from 1 to x squared, so I can use the theorem, right? Now what? So we kind of mentioned this last time. You do the chain rule, right? It'd be natural log of x squared. You can just plug that in like we did before. But now, because this is an x, I multiply by the derivative of x squared. So I get negative 2x times natural log of x squared. Now what's the domain? This is the part we never actually asked. If you go back to the book, this is all it said. And this is all I'm kind of looking for on, if I give you this problem, this is all I'm looking for. But what are some kind of nuances here? This is assuming, when I write this step, I'm assuming x squared is bigger than 1, right? Which means x is bigger than 1 or x is less than negative 1. If x squared is bigger than 1, x is bigger than 1, or it is less than negative 1. Do we believe that one? Now there's one more. So like, if I take a negative number less than negative 1 squared is bigger than 1, right? We believe that part. Could I do x less than negative 1 and use what I had before? I said f must be nice. What happens if you plug in 0? Can I do natural log of, so here this part might make sense, but I have to be a little bit careful. Natural log of t doesn't really make sense when I'm talking about x equals to 1. So I always have to be a little bit careful there. This really says I need to be strictly bigger than 1 or really less than negative 1. If I did something in between, I'd cross over 0. Could I cross over 0 here? And if I started at x squared equal to 0, this integral doesn't make sense anymore. Because I can't plug 0 in. So I also need to be a little bit careful when I talk about that. If I pick any interval x squared to 1, it does actually work out. Once x squared is big enough. So like this part really is coming in, and this is saying this bound must be bigger than this bound. Here when I do that, this x squared must be bigger than 1, or this part doesn't make sense. And typically you only pick one of these. So you'd say for x bigger than 1, or you could say you could do this for x less than negative 1. These are really kind of two separate answers. It depends on context though. Good. Any questions on that? Here's one we didn't really, what's cool about this? Do we know what that antiderivative is? Whose derivative is natural log? It's not one we have there. I'm not saying there isn't one, but it's not one we just know, right? So did I need to do that? That's the part the fundamental theorem was kind of letting us skip here. Typically, when you saw this, you would say, find the antiderivative, plug in x squared, plug in 1, right? Here, I never actually need this antiderivative. So the fact I don't know this doesn't matter. So this antiderivative isn't needed. Change this to y is equal to the integral from 1 to x squared of x cubed times natural log of t. And now I want to again find y prime of x. Did we ever have one where you had an x on the inside? So this one's not quite the fundamental theorem. We always give you something and then never use it. Right? Never talk about what to do with x in the game, right? Any ideas? So in every example, we had x was in the bounds, so either the top or lower bound, right? And we did one where it was in both bounds. And that one's a little bit of a headache, but we can do it. Now what? What's the variable inside the variable? Right dt, what is that? The only variable that matters when I find the antiderivative is t. Does that x have to be inside the interval? That says only look at variable t, right? Ignore everything else. Which means technically I can move the x cubed outside. Do this. Is that believable? When I find the antiderivative, so that says find the antiderivative with respect to t, which means I don't care about the x cubed anymore, right? I can move the x cubed, I can treat x cubed like a constant and move it outside the integral because the only variable inside the integral is the variable t. So this would be a lot harder if I had an x mixed in or could do this. And this is as bad as we get for this course. I can separate these, I can back these from outside. Why does that matter? X cubed depends on x, and technically this depends on x, right?
I thought it depended on t.
It does, but then when I plug in the bounds, the t goes away. So like if you find an antiderivative and plug in the x, there's no more t anymore.
But before the
So when you see this, think of it as a function of x. It is some big function of x. We call it the accumulation function, or an accumulation function. Because mine don't include the bounds. If I didn't include the bounds, I couldn't say that. When you plug in the definite integral, all the t's go away, right? In the end. So like, pretend I do the antiderivative of natural log of t. find the antiderivative, plug in x squared, plug in 1, subtract. Are there any more t's left over?
Don't you still need to know what the derivative is, because it's product rule?
It's product rule. Yes. So when I look at this, I think I have x cubed as a function of x. I have this whole symbol. This really just represents a function of x. It's some accumulation function of natural log on the interval 1 to x squared. But like, when I take that integral, t's get 1. It only depends on x in the end. So it is a product rule, but I'm going to treat it as this is one term, this is the second term. So then what does it become? Derivative of the first term times the second term plus the first term times the derivative of the second term. So what do I get? Now it looks like problems we actually know, right? Derivative of x cubed is 3x squared. This part just stays the same. It is some function of x. I don't really care what it is. That's a fine way to write it. I'm finding what is this based on x? It's whatever that value is. I don't actually have to know it. And then what is the derivative of that? So my goal is to get rid of derivative signs, right? You find the derivative, your goal is to get rid of all the dpx signs. So then what is this last one? How do I find this? Plug in the x squared, then multiply by the derivative by the chain rule. Am I done? This the derivative. When do you stop taking the derivative? All the d over dx symbols are gone. Once all those are gone, this is my function. Anything here would be simplifying, but at this point I've already found it. So it looks a little strange, but this is the derivative. Like we didn't find it, we didn't write this as some a of x term, but it is just a function of x built in, right? So symbolically, this is the derivative. If you plug it, if you pick an x value, plug it in here, whatever this calculates to is the slope. So the new one, if you had x's in the integrand, we might have to do a product rule or some other way to split it up. That's assuming you can split it up. We're not going to talk about the other case. All right. One more of these. Y prime of x for y of x equal to integral from x squared plus 1 to x to the 4th plus 1, natural log of t dt. In all these, I never find an antiderivative of natural log. So I keep the same integrand. I'm really just messing around with the balance. But like we never actually find this antiderivative. It doesn't matter for what we're doing. this, what do I need to do?
ln of, the end of the interval function times the derivative of the end minus the,
Yeah, I did tell you the trick already, didn't I? Yeah. So now I want to convince you based on this theorem, but yes. I did give you the formula last time for where this comes from. That's assuming people picked up. There's 10 up here, and y'all were here probably here last time. You want to come up with it? I want a constant bound somewhere. What would be a good choice?
zero or yeah.
0, I run into troubles when that's log is 0. So I'm going to pick 1, and the reason I wanted to split this up is to tell you why you pick 1, or why that's a good choice. I can do that, right? Pick a number. Technically, we usually say in between, but you can touch out a little bit. But I pick a constant. And now, why would I pick this constant? I can integrate from 1 to x squared plus 1. I'll put a negative sign out here. And then I could add this derivative from 1 to x to the 4th plus 1. Natural log of t dt. Why did I pick 1? You always want that lower limit to be a true lower bound, right? X squared plus 1 is always bigger than 1, or greater than or equal to 1. X to the 4th plus 1 is always greater than or equal to 1. So now it fits this idea up here. I can do this as long as x is bigger than my lower endpoint. This bound is always going to be bigger than my lower endpoint. So there was a 0 wouldn't quite work because I worry about discontinuity here. But by picking the number 1, it is something that, as I rewrite this, is a nice lower bound. So I know that part's not getting in the way. So then what do I get? So this would be negative natural log of x squared plus 1 times derivative at the top plus natural log of x to the 4th plus 1 times derivative at the top. And now it looks like that formula you mentioned. Plug in the top, multiply by its derivative, subtract, plug in the bottom, multiply by its derivative. So it works out the same way. If we're worried about domain issues, like when can we actually do this, you have to be a little bit more careful. So we did this example last time, real quickly at the end of class. I wanted to mention a couple words about it. Last time, I guess that was what, a little over a week ago. So f prime of x is 2 cosine of pi x. And f of 2 is equal to 6. So we mentioned this where, I don't remember this exact example, but I mentioned one where you could do something like this. What happens here? F of x must be an antiderivative, right? If I give you the derivative and say find the original, it just means find the antiderivative. So if you did that, you would say f of x is this antiderivative plus c. I don't know what c is. And then how do you find c? Plug into here. f of 2 is 6, that tells me c must be some value. So we ran through an example where we talked about that the other time. So from here I can get f of x is, what is the antiderivative? Is that what's up? Derivative sine is cosine, multiply by pi. Yeah, that works out. They'd have to be plus c, right? So then you could say 6 is equal to f of 2. So 6 is equal to 2 over pi. That's why I plug in 2. Sine of 2 pi plus c. Sine of 2 pi is 0. So c must be 6. So I put all that together, f of x must be this. If you find the antiderivative, it's only up to a constant. I don't know what the constant is, right? I can't tell you, I can tell you the form of f of x. F of x must have this form, but I don't know what the number is. How do I choose the number c? Choose it so that this happens. So we did something like that very quickly. I wanted to mention another way that this gets set up. This is one that, the way we did this isn't exactly using the fundamental theorem in the way that it's really written in the book. So, we're really plowing through the theorem. What we say is this. I want to make it look like a theorem. I would say this. F of x minus f of 2 is the same as the definite integral from 2 to x of f's derivative. Is that a true statement? It really is how we talk about definite integrals, right? Why would that be useful? What is f of 2? 6. That is the definite integral from 2 to x of, what is f prime? 2 cosine of pi x. So I'll replace the x with a t. So this is the more canonical way this one gets set up. Instead of, I've always done it this way, find the antiderivative. I know it's wrong by a constant, find the constant. Or you can write it this way, and the reason they do this is it fills in that value perfectly. Like I don't have to solve for a constant anymore. When I did this, all I used was the fact I knew the derivative. I ignored this altogether, right? And then I used this information in secondary to solve the rest of it. Here, I plugged in both pieces of information at the same time. Everything is accounted for. So then what is this definite integral? That's the 2 over pi sine of pi x, or pi t, evaluated from t equal 2 to t equal x. So I get 2 over pi times sine of pi x minus 2 over pi times sine of 2 pi, which is 0, so I get this. So then what happens? What was my goal? I wanted to find a function f of x where both of these are satisfied. So now how do I find f of x when I did it this way? This says f of x minus 6 must be exactly this factor. So just move the 6 over. So now f of x is equal to whatever I just found plus 6. So it basically solves directly for f of x. Every book I read is always one of these two different ideas. So I want to make sure I talk about both. One more big concept I want to talk about today. Let's say we have this function. So we have this one. So here's some function f of x on the interval 0 to 6. Basically looks like quadratic opening downwards. Except I have a very bad day. Actually, this is 5. I want to be consistent. Alright, so I want to define a of x is equal to the integral from 0 to x of f of t dt. And eventually I'm going to redo this with f of x is the integral from 4 to x of f of t dt. I can do either one, right? So, first question. When is a of x bigger than 0? So what would happen there? A of x is the integral from 0 to x, right? So, say I pick x here. A of x would be this area. If I pick x here, A of x is that whole area. Is that positive or negative? So that's the definite integral from 0 to x. I'm above the x-axis, so I'm getting positive areas. And then what about when I plug in 4 for x? Still positive, right? What if I plug in 5? Is this area, do I expect this whole definite integral to be positive or negative? So it would be this area minus this area, right? This area doesn't look as big. So ends up, I would say, this is positive on the interval 0 to 5. And I can include 5. Would I include 0? So if I find A is 0, what do I get? A of 0 would be the definite interval from 0 to 0. Is that value positive or negative?
It should be 0.
It would be 0. So is that positive or negative? Neither.
What's number?
0 is 0. 0 is not positive or negative. So I can't include 0. So I do have to throw out the number 0. Otherwise, it's always positive. Once I move past 0, it starts being positive. All right. When is A of x increasing? So that means A prime of x must be positive. Right? Well, what is A prime of x? Just f of x. How can I say that? A prime of x would say take the derivative of this. What's the derivative of this? Plug in x for t. So when is that positive? Zero to 4. Does that one make sense that it stops at 4? So if I plug in 0, I get 0. When I move this way, my area is positive. It's getting bigger every time I move a little bit to the right. So the area stopping here is less than the area if I stop over here. What happens when I get to 4? If I plug in an x value bigger than 4, I get negative numbers. So I start subtracting. So the area is getting bigger and bigger until here. Now I have to start subtracting some off, so it starts getting smaller. So that means it is switched to decreasing. Right? I was increasing all the way into here. Now I start subtracting these values off. It starts, so it accumulated up to some big area here. Now my area is getting smaller. So I went increasing to decreasing. Now that's decreasing. Now it's getting smaller. I'd have to stop. I'm increasing up to 4. Okay. What about concave up? So that means a double prime is positive, which tells me that prime of x is positive. What interval does that happen? Is 0 to 2. The slope of f prime is positive up until here, then switches to negative. So what that's saying is my area is accumulating faster and faster, and after this point, it's accumulating less quickly. Which makes sense, right? When this starts getting smaller, as I add a little bit more, it's getting bigger, but not as fast. So that's really a change in cavity. When is, I have the full solutions I'm going to post after class, but when is f of x positive? If I start everything at 4, f of 4 is equal to 0, right? F is the definite interval starting at 4. So the interval from 4 to 4 is 0. What about f of x for x less than 0? If I start here and move this way, so this would be the integral from 4 to x. So f of x dx. If x is negative, or sorry, for x less than 4. If x is less than 4, I should really put it on the bottom, right? It's a lower bound. We always think the lower bound is the smaller number. So integral from here to here is always a positive number, but it becomes negative because of this. And then what if I'm bigger than 4? If x is bigger than 4, I start here and I find some area below the x-axis, so it's negative. So f of x is always less than or equal to 0. It's never positive. What about, we'll talk about this one real quick and then we'll go increasing. So what is f prime of x? I could say it's the same as f of x for x greater than 4. If I'm less than 4, I have to be a little careful. So this is the derivative from 4 to x. But what do we say if x is less than 4? I should really do negative the derivative from x to 4 of f of t dt. That change in there? Then is this going to add with it? It's going to be positive or negative. What is f increasing? So let's say x is here. I get a big negative number, right? So if I'm moving it here, x to 4, that's a big negative number. What if I make x a little bit bigger? It's negative, but less negative. So is that increasing or decreasing? Increasing. So if you check, f prime of x is still a little f of x. So you got the same answer. And then what about concavity? Well, if the derivative is the same, second derivative would be the same. So what's the only thing that mattered, or the only thing that changed was this first one. What am I positive or negative? All the slopes are going to be the same. All right, that's all I'm going to get to here. All right, sorry about that. Maybe we'll finish early once or twice this week. Myself. All right, definitely out of time. See y'all tomorrow. Make sure you get this homework finished. Help center's open. Make sure you email me if you have questions.